Hello guys, I'm Introductory and today I'm going to demonstrate an introductory layout technique of 0.25 GaN HEMT IC process. This is a commercial PDK IC process and I intentionally chose this simple schematic because it's always better to demonstrate anything with a simple example rather to make it complicated. What we see in the schematic is not what we have in the real-world IC, because the transistors are symbolized in a schematic view, but they are not actually like that in the real world. So schematic is just kind of symbolic abstraction of the real-world IC component, right? So let's go to the ADS layout editor in order to initiate this layout of this schematic. So let's open the layout window. Well, these are the layers of the GaN IC process, and you can see the IC process layer view, metal 1, metal 2, and they are connected by via 2. Okay, so a simple IC process. Because in CMOS we have even 9 to 11 layers, even more than that. So we would like to define the transistor, and let's define the number of finger to 4. And unit gate width to 200 micrometer. Okay, now let's define a resistor, a very high resistance, meso resistance. So let's decrease the width. Okay, you can ignore this line. This is just a connection indication. It will disappear later. The best layout is a compact layout, so I'm placing the component near to the transistor. And we need a high capacitance. Okay, all right. So very simple, right? One transistor, one resistor, and a cap. And now we would define a very large inductance at the drain line. So let's rotate. So, okay, near enough. Okay. Now you define another capacitance. So it should be 150 and length 150. Okay, you can delete the old one. Okay. So these were the components shown in the schematic. So it's very simple, a few components, one transistor and a couple of capacitor, and an inductor and a resistor. Now we'd like to join the node of the components. So we would join by metal 1. You can increase the width of the trace, like 50. Okay, so this connection will be from gate to the resistance, and we need to also connect them. Okay, let's connect it in this way, and let's delete this one. And then the drain connection. And this is the drain of the transistor, and the cap can be connected in this way. There are some DRC rules. The purpose of this video is to provide you elementary training on layout, so I'm not discussing the DRC rules. But without DRC clearance, we cannot fabricate any chip or any IC. And we need to maintain a certain distance, which is based on DRC rules. But you can ignore that at this stage. So this is the view from the real world. Actually, when you see the IC through a microscope, this is kind of top view. So what you are watching is the top view of the real world IC on the computer screen. And truly speaking, layout can be much more complicated than this one, because this was a very simple layout. But for example, this is a layout of a GaN amplifier designed by me. And you can see this layout has a couple of GaN HEMT transistors at the center and a lot of inductors and capacitors. And there are also GSG and PGP pads for providing DC and RF signals. So this layout is very complicated relative to the previous one that we used for the initial training. And there can be layout containing thousands of transistors. So in that way, in that case, we use basically hierarchy-based design. If you are familiar with cadence virtues, so you understand what I mean, right? And anyway, so this IC of the duality amplifier only takes an area of a few micrometers, so it's impossible to discern the individual elements of the IC in naked eye. We always use microscope to measure an IC on the probe station, and by the help of microscope we can see the real view of the IC. And I have another video which shows how to measure an IC on probe station by using microscope and RF and DC probes. So this is the fabricated real IC of the duality amplifier that I just showed a moment ago, and we fabricated it using a commercial foundry. And this is a micrograph taken directly from the microscope when I was measuring the duality amplifier. So the IC world is kind of very interesting because we always deal with the microscopic world, and the world is very, very different from the world we live in. There is so much parasitic inductance and capacitance. If the frequency gets higher, the whole response of the IC changes because of that parasitic inductance and capacitance. Anyway, so thank you for watching my video. If you find it useful, don't forget to press like button and please subscribe to my YouTube channel.